Okay, so this is section 3.2 of Math 146. There is a lot of stuff to cover in this section. This will definitely be a multi-video lesson, and I think we're actually going to end up combining some of the stuff from this with what would be in 3.3 as well. Um, so we'll see how all this works out because I think explaining some of the stuff that you'll need for 3.2 really is found in 3.3, or at least can be made easier by 3.3. So what we're going to start off with is what again should be a little bit of review though. We're going to be talking about how to compute the values of trig functions. And in order to do that, you have to know kind of the basics, which is your sine, cosine, and tangent. And all of this stuff is based upon right triangle trigonometry. So we'll just do a very, very quick review of the parts of a right triangle. So the right triangle, this part over here is your hypotenuse. And then you have basically two legs of the right triangle. And depending upon where your angle is located that you're interested in, for our example, we're going to put theta down here at the bottom. You have what is considered to be an opposite side from that angle, which is the one that is across from it. And then you have what is considered to be an adjacent side because it actually physically touches the angle. So those are your three parts of the triangle. And again, this should all be review. Sine of the angle is said to be the ratio of the length of the opposite side over the hypotenuse. That's actually how it is defined. And these are numbers. Now these are lengths. So remember, it's the length of the opposite side divided by the length of the hypotenuse. Cosine is defined to be the adjacent side over the hypotenuse. And then tangent is defined to be the opposite side divided by the adjacent side. Again, all that stuff should be reviewed. That's way back to geometry from high school or whenever you took it. Definitely should be something you're familiar with. There are three reciprocal functions, which I'm going to go ahead and list out here. You have the reciprocal, which basically means that you're going to flip over the fraction of sine, which is called the cosecant. Let me write that so it looks better. Cosecant, which is CSC as an abbreviation. And that is literally going to be flip over the ratio. So that would be the hypotenuse divided by the opposite. Cosine's reciprocal, CSC, there we go. Cosine's reciprocal is the secant, we abbreviate that SEC, of theta. And again, it's the reciprocal, so hypotenuse over the adjacent. And then tangents is the cotangent, abbreviated COT, and that is going to be the adjacent divided by the opposite. All right, so that is your very, very brief review of geometry when it comes to the ratios of sine, cosine, and tangent. Most people have been taught some kind of acronym such as SOHCAHTOA, which if you think about it, SOHCAHTOA means that sine is opposite over hypotenuse. There's the S-O-H. The ka part is C-A-H. So ka, and then toa, T-O-A. Just gives you a nice little easy way to remember this. S-O-H-C-A H-T-O-A, SOHCAHTOA. There isn't really one for the reciprocals. You just need to know which function has a reciprocal, which one it is, and then flip it over. There are all kinds of different ways to kind of memorize which ones go with which ones. The one thing that I always like to think about, and this helps, again, for future classes, calculus and so on, that every function that you see here, there is a co-function. For example, you have cosine cotangent, and cosecant. There is a non-cofunction as its reciprocal. So cosine can't go with cosecant because they would both be cos. So cosine has to have its reciprocal as secant. Sine then would have the reciprocal as cosecant. So you see how every cofunction has a non-cofunction. The only one that tends to actually make sense is tangent and cotangent because they just kind of, because they're the same name basically. One's co and one's not. All right. So that's just a nice way for you to remember how to do stuff like that. Um, we have different types of angles. It's just some real quick vocabulary. If you have an acute angle, that is an angle that is less than 90 degrees. You have an obtuse angle, which is an angle that is greater than 90 degrees. And then you have a right angle, which is 90 degrees. So just vocabulary there, just to make sure we've got that down. All right, so we have talked about the 6 trig functions. We've talked about their reciprocals and how to find the values there. If I were to give you a triangle with 2 sides, let's go with this. So if I was just to draw a triangle, oops, that is horrible. And I were to give you 2 sides of that triangle, here is your angle. Let's say that that's a 3 and that's a 5. Well, you can find the missing side because we should know the Pythagorean theorem at this point. A squared plus b squared equals c squared, where a and b are the legs and c is the hypotenuse. So you could plug that stuff in. I'm not going to write that out. This should be something you know. But you would ultimately get the missing side over here to be 4. And then if I asked you what is the sine, the cosine, and the tangent, and all the other 6 trig functions based upon that, you could very easily list them. I'm not going to list all of them, but you would say that the sine is the opposite side, which is 4, over the hypotenuse, which is 5. And then if you wanted to do the cosine, it would be the adjacent side, which is 3, over the hypotenuse, which is 5. And then tangent is 4 over 3. I'm not going to write that one out. If you wanted to do the reciprocal, very easy. The cosecant is the reciprocal of sine, so you just flip over the fraction. It is 5/4. Likewise, for cosine, the reciprocal would be secant, so that would be 5/3. Very easy way to be able to figure out some of these values. So let's write down some of the identities that we're going to need, because these are very important from here on out. You have what are called the reciprocal identities. We just talked about the reciprocals. Reciprocal identities. And that says that cosecant of theta is equal to sine flipped over. Well, that's the same thing as 1 divided by sine of theta. Likewise, you could have written that as sine of theta equals 1 over cosecant of theta. Either way it works. So then secant of theta would be the reciprocal of cosine. And tangent of theta would be the, cotangent, let's write it that way since we're using the other 3, would be the reciprocal of tangent of theta. So those are your reciprocal identities. We also have what are called the quotient identities. Quotient identities. And the quotient identities, there's really 2 of them that we're interested in here, is that tangent of theta is the exact same thing as the sine of theta divided by the cosine of theta. when we actually get into the circle and how the circle actually equates to all this stuff, this will hopefully make a lot more sense. And then cotangent of theta, well, since cotangent is the reciprocal of tangent, you can literally just flip the sine over cosine upside down there and get cosine over sine. And of course, of theta. It is very important, since we're using trig functions, that you have an angle attached. Just writing this doesn't mean anything, or just writing that doesn't mean anything. You have to have some kind of an angle attached to it. So make sure you get in the habit of writing that, even though we think in our heads, oh, cosine and sine, we just don't say it that way. Okay, one of the other very, very important identities are the Pythagorean identities. This is probably the most important one. You take sine squared of theta and add it to cosine squared of theta. That will always equal 1. The important thing there is that you notice that both of those are theta. They are the exact same angle. So if you take whatever the angle is that you're given, and you take the sine of that and square it, then you take the cosine of that and square it and add those two things together, you will always get 1. Okay, that's probably the most important of the Pythagorean identities. Now, technically, there are two other Pythagorean identities. You have the Pythagorean identity that says tangent squared of theta plus 1 is going to equal secant squared of theta. You also have another Pythagorean identity which says that cotangent squared, let's write it slightly differently, 1 plus cotangent squared of theta is going to equal cosecant squared of theta. I try to tell people you really don't need to memorize these. If you have a great memory and you can memorize them, go for it. But you can develop the two Pythagorean identities in blue as long as you understand the first one. And the reason for that is because you can do a simple division, assuming that you understand the properties that we had just above it as well. So let me kind of bring these back up so we can use these. All right, so the way you would develop it, I'll develop the first one, but I'm not going to develop the second one, is, so if you take the original equation, sine squared theta plus cosine squared theta is equal to 1. And algebraically, if I decided to multiply everything on one side, then I would multiply everything on the other side by exactly the same thing, and it's okay. Well, we can divide. We can do the exact same thing, but we can use division. So what I'm going to do is I'm going to divide every term on both the left and the right, in this case, by cosine squared. So I'm going to take and divide every term that's supposed to be in green by cosine squared theta. Okay, haven't done anything wrong, maintaining the balance. So now you can use the identities, the quotient identities, and the reciprocal identities to simplify. So sine squared divided by cosine squared, if you look at the one on the quotient identities, would be tangent squared, because sine divided by cosine is tangent. Cosine squared divided by itself, of course, is 1. And then 1 divided by cosine squared, well, that is your reciprocal identity for secant squared. So we've now just developed the second identity. And if you're thinking about it, well, then how would I get that third identity? Well, instead of dividing everything by cosine squared, I would have divided everything by sine squared, and you end up with the third identity. So here you go. These are the things that are important. This one right here is the most important of your Pythagorean identities, because you can use it to develop the other two. Again, if you can memorize them, awesome, go for it. My memory is not the best, so I always try and figure out ways that I can figure things out if possible. All right, so those are probably all the identities that I think that we're going to need for now. There are several more. identities that we'll be using in the future, but I think that's probably what we really need to have for right now. All right, so let's do an example of where this might be useful. So a lot of times you might be given a trig value, and it might say something like, they're going to tell us that sine of theta is 1/3. And what they want us to do is they want us to find all of the other 5 trig functions values based upon what they just gave us here. There are going to be times where there's going to be some special values that make this a little bit easier, but for now, this is the method that we're going to use to start this off. Because we know that sine of theta is 1/3, the very first thing I'm going to do is I'm going to sketch a triangle. Sketch a right triangle. Doesn't have to be in any particular method. This is just kind of the way I do it. As far as like which way you draw your triangle, I almost always put my theta on the bottom. It's just most of the time it's easier for people to understand. So if it's sine of theta equals 1/3, well, we know sine is the ratio of the opposite over the hypotenuse. So that means that the numerator is the opposite. Well, that's the opposite side. That's 1. The denominator represents the hypotenuse. So that is here. That's 3. If I want to find the other 5 pieces, the other 5 trig functions, I'm still going to need to know what the adjacent side would be. So we'll use Pythagorean theorem. This time I will write it out. We know that 1 squared plus whatever variable you want to call that denominator, I'll just call it b squared in this case since we typically use a, b, and c, is going to equal 3 squared. So that means that b squared is going to equal 9 minus 1 if you subtract 1 on both sides, or 8. So then b is going to be the square root of 8. Okay, the square root of 8 can be simplified, but for right now we're going to leave it as the square root of 8. All right, so now that's going to give me everything that I need to find the remaining trig functions. So we still need to find the cosine, the tangent, the cosecant, the secant, and the cotangent. Okay, notice I didn't write the sign in there. I could have brought it down and written that in there, but I don't need to. The easy one to do is cosecant. Given the fact that they told us that sine was 1/3, since I know cosecant is the reciprocal, I'm just going to take that fraction and flip it over, which means that the cosecant is 3. Again, that's supposed to be in green. Why is that not writing in green? There we go. So the cosine then is going to be the adjacent side over the hypotenuse. Well, the adjacent side to this triangle is square root of 8, and the hypotenuse is 3. So we're going to get the square root of 8 divided by 3. What does that make the secant? Well, that means you're going to flip it over. So that would be 3 divided by the square root of 8. And then the tangent is the opposite side of the angle divided by the adjacent. So that's going to be 1 divided by the square root of 8. And then the cotangent is the reciprocal of that, so we flip that over, so it'll be the square root of 8 over 1, which is just the square root of 8. Now, these are perfectly acceptable answers. I do know that sometimes these computer programs, MyMathLab and so on, will make you rationalize the denominators. Again, this is mathematically correct what we have here, but since I do know that it's going to be required in some cases to rationalize the denominator, let's make sure that we can do that. So the ones that have to be rationalized are secant and tangent. So if you take secant, you're going to have to multiply the numerator and denominator both by the square root of 8, which will leave us with 3 times the square root of 8 on top. And then, of course, the square root of 8 times itself leaves you with just 8. And I am not sure if it's going to make you simplify the radicals. If you do need to simplify the radicals, then that will change the overall simplified answer. So again, I'll show it in this case but I don't know that it's going to be necessary. So in this one, I'm going to bring this down here. It'll be 3, and the square root of 8 does simplify because the square root of 8 can be written as the square root of 4 times 2. And since we know that the square root of 4 is 2, that'll come out and get multiplied times the 3 on the outside and still leaves a square root of 2 on the inside. And technically, we'll get 6 times the square root of 2 on top, but we can factor or divide a 2 out of both the numerator and the denominator, which will leave 3 square root of 2 over 4. So that would be the most simplified version here for the secant if you are required to simplify and rationalize the denominator. Again, I am not necessarily going to be a stickler for that because I don't think it's absolutely necessary to do. However, you should know the process and you should know how to do it. Tangent's much easier. You multiply the numerator and denominator by the square root of 8, and that leaves you with the square root of 8 over 8. Again, if you have to simplify the radical, you can do that. I believe that would leave us with square root of 2 over 4. The other ones do not need to be rationalized, but they could be simplified because the square root of 8 can all be simplified. Again, all that is probably much more than we needed to know. This right here, for me personally, is an acceptable answer. I am perfectly fine with that because mathematically it is correct. There are reasons to rationalize, not something I am going to stress on right now. Again, your computer program might have you do it, so just know how to do it. Okay. I think that's probably pretty good for this video. We're going to come back with a second video, and again, there may be even a third video in this case. We're going to talk about the idea of being able to compute some of these values using reference angles and what reference angles are, and go into some further detail about circles.